Next in line is our colleague Ana Oliveira from Portugal. Ana, are you here?
Yes, I am.
Yes.
Hello.
Hello, Serbia calling.
Yes, Portugal replying.
Thank you, Ana, for joining our workshop about extreme heat. As mentioned at the beginning, actually it was in Serbian. I mentioned to our students and colleagues here that we are interested in extreme in our country, but also I wanted to see if one of my colleagues would like to present some results from abroad, especially for Europe. So we are, of course, at least in temperature sense, we are part of Europe. And also we have Manavi from India. So in this regard, I'm very happy. And once more, thank you, Anna, for your time to show your excellent work. We have here very prominent young minds who are studying geosciences, and part of them are actually studying GIS. And I mentioned that you rock in GIS, in load sensing, and applying different very state-of-the-art methods. And in this regard, I think this will be very useful for all of us, but especially inspiring for these young geoscience minds here in Novi Sad. So now I give the floor to you.
Thank you. Thank you so much, Dragan. It is a pleasure to hear you again. Also, hello to Jelena, who I met in Portugal a couple of weeks ago. And I'm very happy to be, hello, I'm very happy to be here with you. And I hope you do enjoy my conversation. Please feel free to reach out should you have any question, any doubt, if you want to share data, etc. Because I'm a very straightforward person and you can feel free to contact me at any time. So I'm trying to start to share my screen now. Okay, so screen is sharing right now, right?
Yeah.
Okay. So I'm going to provide a presentation that has an overview, a mixed overview between what I did in my PhD and what I'm currently doing at Plus Atlantic. Actually, my background is architecture and spatial planning. So I'm kind of an hybrid. I traveled from making projects for buildings, design projects for buildings, to studying urban planning and sustainability practices in urban design. And then I traveled a bit further in my PhD for remote sensing and geospatial analysis. So this is just to give you a background of why my research journey is so diverse and not extremely focused, unlike other researchers. So the motivation for my research was basically that in Portugal, as I believe it's in Serbia the same, from what I gather, we have climate change prospects of more intense heat waves and more frequent heat waves in the future. We also have some struggling with aging population, which is a more sensitive group to heat-related hazards. And we also have constraints in terms of local climate adaptation capacity, because Portugal is not a very rich country and municipalities have low budgets and they struggle in terms of scientific expertise and money to implement solutions. So considering this, the challenge I put myself through was to do something that was efficient in terms of the techniques to be employed, something that would be scalable to other locations, especially in Europe. So I'm using only open data, and something that could be replicated at a low cost. Considering this, I delved into more empirical strategies and statistical strategies instead of, say, EnviMet or other numerical models, because they are typically very hard to implement on the municipalities with people from the public sector. So I basically focused on machine learning, statistics, to develop heat-related mapping strategies in terms of heat waves exposure in several cities. I'm going to present just a couple of the models that resulted from this work. The rationale or background in terms of heat waves you already know, and it has already been presented today. So we know that heat waves have an impact in terms of health that is statistically significant. It can be translated into costs, costs in terms of life and healthcare as well. It's a silent killer in the sense that, unlike COVID or cold waves, the response has a bit more of a lag, and sometimes it's difficult to distinguish mortality from heat from the covariates in terms of the background of the health conditions of the elderly, and also, at least in Portugal, during the summer, there is not much demand in terms of healthcare. So a spike in the healthcare demand is not as visible as during the winter. So a spike during the cold season, it is already mentioned in the media. During the summer, it's more difficult to have public attention because the background average values are much lower. So a spike is still within the capacity of the healthcare, and not much attention is given. Nonetheless, because heat waves are increasing, it is a problem, and it is a problem that probably is going to be aggravated in the near future. And then we have the urban heat island effect, which increases heat in urban areas. It also depends on the daily cycle, etc. But it is a stressor in terms of heat exposure because it is where people live, and also the artificialization improves, or magnifies the heat exposure. In my research, as I said earlier, I'm not a climatologist from the start, or a geographer, physical geographer. So I tend to choose more simple approaches. And this is one of the reasons that led me to the excess heat factor. The excess heat factor, in total honesty, cannot be called as a biometeorology index in the sense that it only accounts temperature. It does not account for humidity, clothing, or wind stress. But the reason that underlines the development of this index, it is by Australian authors, is the fact that in locations where the main drive for heat stress is temperature and not humidity, and this is the case in Portugal, the summers are quite dry, it is sufficient to account for temperature if we want something that is an indicator that is easily implemented in terms of national surveillance, and it is easier in terms of computation, in terms of input data, and it is a reliable proxy that does not replace biometrology indices, but as a complement or as a first approach towards heat exposure. I can explain further the excess heat factor if you have curiosity on it, but for now, I think it suffices to say that it is basically a multiplicative index that multiplies the long-term anomaly in terms of climatology to the 90th percentile with the short-term variation of air temperature. It uses daily average, and the reason for the authors to choose daily average is because in dry climates, daily average increases already have embedded the increase in the minimum temperature and the maximum temperature as well. And so according to the authors and the research they published, it is sufficient to account like this, and it has showed significant accuracy in providing a proxy for mortality. Here in this plot, you can see the relationship between the excessive factor in Portugal and an occasion of excess heat related or overlapping an increase or spike in mortality. Just to give you a notion, in Portugal, typically daily mortality numbers are greater than 600 during the winter, and this is to say that these values that you see here during the summer, the background is so low that this is the reason why not much attention is given, although the scenario is changing in the last years. So the first work I did was to basically rank European functional urban areas, metropolis, in terms of the excess heat factor, because this index had not been calculated to Europe. I used the CleanPact R-based tool, which is the tool developed by the authors to calculate automatically not only the excess heat factor itself, but also annual summaries for trend analysis, etc. And basically translates the intensity of the excess heat factor, which is a quadratic function, so it's degrees Celsius squared, into summaries of frequency, intensity, and duration per year. And these annual summaries using the EOBS greedy dated as the input, spanning from 1950 to 2018, It was this output from CleanPact is basically the impact for what I will present next, which is the pixel-wise linear trend analysis to see how this excess heat has been changing in Europe, and also to rank the exposure in the functional urban areas in Europe. From the results, you can see that the spatial patterns are not that different from what we gather from other indices related to climate. You can see that in terms of mean magnitude, which is this one above, you have greater values in the northern and central part of Europe because of the northern or latitudinal amplification. You also have some kind of that in Portugal as well. You have positive anomalies mostly throughout Europe. But if you look at the maximum heat wave intensity, which is translated into a maximum heat wave amplitude index per year, the results are much more striking. And as you're going to see next, the significance of the trend is also much more interesting to analyze. Then you have this, which is the excess heat factor severity. Because we do have a gradient in terms of thermal amplitude going to the northern part of Europe, one has to divide the maximum intensity, which you see here, per each 80th percentile to get a normalized severity index that spans between 1, 2, 3, and it's normalized. It doesn't have units. And what you see here is more or less the reverse scenario compared to this, in the sense that you see that despite lower maximum intensities in excess heat factor, for instance, in Italy, you do have very significant excess heat factor severity in the latest decades, and you do have a very significant anomaly. So going forward to the trend analysis, you have positive trends throughout Europe in most locations. Of course, the Mediterranean region and the central parts of Europe do have the greatest values in terms of most of the indices, frequency, duration, and maximum intensity. The potential surprise here for some of you is that no significant changes do occur in the mean heat wave intensity when it is calculated based on the excess heat factor. The implication of this is that the extremes on average are not changing in intensity significantly, but they do in terms of the maximum intensity, which has an implication in terms of how the extremes are shifting, but not the means. Then you can plot the distributions in terms of bioregions in Europe, and you can see how these linear trends behave across these regions. You can compare, for instance, the Mediterranean region in which I live with the Pannonian region in which I believe you do live, and the very positive and significant linear trends you see here, especially since the 80s. This is a new index, but I mean, the conclusions are not that different from the ones you presented earlier with observational data in Syria and with other observational studies you see with gridded data in Europe. The latest part of this research was to produce a kind of index of exposure. So there are several approaches to produce an exposure index. You can do something like a cumulative exposure in which you add probability of a given hazard to the sensitivity of the, say, population or buildings or whatever that is exposed to that hazard. You can also account for adaptation capacity if you want to go to vulnerability instead of exposure. Here, my rationale was to follow previous experience that proved that the multiplication factor is much more similar to how mortality and health impact behaves. So it's a multiplicative function of the population at risk per the hazard. I did normalize the population numbers because in Europe, the distribution is quite exponential. Otherwise, we would have very high risk in very dense capitals such as London, and then no risk whatsoever in the rest of Europe because the number of population is very different. But by normalizing it, you can produce an order, a linear order in terms of cities. And the results are expressed in this paper, in this plot, in which you see the probability of severe heat waves based on the excess heat factor as the background, and you see positive throughout most Europe probabilities above the 50th percent, and you can see the ranking of cities also ordered here. You can check the full list of cities in the paper because it spans more than 800 functional urban areas. A second study that was related to this was focused on Naples. Here, the challenge was to see whether there is a relation between the atmospheric urban heat island and the thermal images we see from space, and also land use, land cover. A first step towards this was to compute local climate zones, which were presented earlier, as well as a framework. And to do this, I chose to use Copernicus data as the input, mostly urban atlas, imperviousness degrees, and the tree cover, because this is openly available data. It is already validated, so I don't have to validate, the shape files, because this is in vector files, the urban atlas. Again, so I just have to validate the reclassification, and it is a more efficient way to produce what I wanted, which was land use, land cover, local climate zones at the mesoscale. So basically, I did this conversion in a previous study, and then I checked for land surface temperatures back then from Landsat 8. I know that there are new sensors available, but this was the most promising open sensor, thermal sensor back then, and fetching diurnal land surface temperature for Naples. The reason to study this in Naples, and I'll study it for Lisbon, but here I'm discussing Naples, is because in Southern Europe during the summer, you have very dry patches of land where the green infrastructure is. So the soil becomes barren or the grass is very dry. And this means that unlike northern countries that have cities surrounded by very green nature, you don't see it in thermal imagery during the day, because the barren soil is already very warm during the day. And as you can see, if you compare the left-hand side and the right-hand side maps, you don't see the city in the thermal signature. This is already the land surface temperature, so it's not the brightness temperature from the sensor directly. It has been converted into LST, and you don't see the city of Naples here. And the reason for that is what I have disclosed before. And also, if you see here the plots from the local climate zones and diurnal surface urban heat island, if we consider the rural temperature as the background, you see that, yes, tree-covered areas are cooler, but the spread is huge, and you don't see the same in other non-dense tree coverage classes such as B, C, and D. But then you have nocturnal imagery. The problem here is that you do not have this imagery available at all times. So basically, I got lucky because this image was available back then in the Landsat repository, but usually there's no nocturnal LSTs available in high resolution. So this was basically getting lucky and a one shot. So my rationale was, if here I can see the surface urban heat island, which you can see here also, this is the statistics from this and these maps together, maybe I can use other sensors and the diurnal fluxes to replicate synthetic LST during the night and produce time series. So this was the motivation, to replicate this image that I know that I will not have in other days, and replicate it by synthetic thermal imagery. So these are images from other sensors, from Meteosat. Here you can see the same pattern, but in very low resolution pixels during the day. And then you can see like a shadow of what the urban location is during the night. But of course, the resolution is very, very, very low. So what I did was to compute the diurnal fluxes based on the diurnal imagery and the local climate zones. Here, the process was following the one published by Professor Hebnard Parlow. I did not say invented myself. I followed the equations that have been already validated by him. And what I did in terms of novelty was to put this together. So in terms of the latent influxes, you can see here the storage effluxes and the sensitive effluxes. You can see here the storage ones, and then use these as proxies for the nocturnal imagery. So again, these fluxes are not calculated with the image from the night, are calculated from the image during the day. Then I put this together in a random forest with the diurnal imagery and the local climate zones. And so basically this is the training data set. I also use the hourly cursor satellite imagery from the Meteosat. And what I get from using a random forest approach is a synthetic imagery that replicates the LST. Of course, I did some training and testing split in terms of the data set, so I did not use it all. Here you can see the results between the observed LST and the predicted LST. And although there are some differences, you can see here the errors. The errors do not show a spatial pattern or clustering, which is good because it means that they are kind of random, which is what I wanted or what is desirable. And the R-squared is very promising for this particular day. Unfortunately, I was not able during the PhD to replicate this to other cities or to validate this during the time series. But I think this is an interesting first approach with promising results to pick up and go forward with this. So later on at the place where I work now, I work at a collaborative laboratory called Plus Atlantic, and the focus is more into applied research. So here the aim is not to develop new models or new solutions or new scientific advances just for the scientific sake, say. What we want is to make tools for the society or for the private sector. I mean, something that can go to the society and become useful. In this respect, we have built the Coast Sense project. It's an internal project. It has not gotten funding from competitive calls yet, but we are searching for that, and we have already submitted some calls. We are waiting for replies. And basically the idea is to produce a digital twin city using the metropolitan area of Lisbon as a case study. The digital twin city approach is basically to have a platform, WebSig, if you will, as you have seen so many, but using geospatial data on environmental and climate hazards to produce early warnings for people to check how their neighborhood compares with other neighborhoods. And the scientific challenge here is to produce models that downscale the official forecasts from weather and environmental parameters to a higher resolution that is more meaningful to the citizen or the public sector. In terms of temperature, this is a snapshot in Lisbon. Lisbon during the summer is mostly characterized by dry patches of land and northern prevailing wind. We call it nortada, and it has to do with our location near the Atlantic. Here is the city center of the capital, but you can see how the urban sprawl has growing throughout the outskirts of the capital. And maybe it's not that visible, but you probably will believe in me when I say that here the urbanite island in Lisbon is mostly a function of the duplicate effect of the natural geography, because it's sheltered from the northern winds due to these higher grounds here, and also due to the artificialization. So we have a double effect that can be the cumulative heat signal from the urban existence and the geographical or landscape context. We also have some observations, but very sparse. The green ones are official from the weather services, and these blue ones are from the municipality of Cascais, which was a partner in the earlier developments. And these are observations from Netatmo. Netatmo are devices that you can buy off the shelf from a private company. They are implemented in an Internet of Things approach, and we can have access to their data via API, if, of course, the owner provides this data to the platform. The problem with these sensors is that they are not, of course, as accurate as official meteorological stations, and sometimes citizens do not put them in the best places. They are not well taken care of. So you have to produce some kind of very strict quality control strategies. We used strategies that are published in the literature by Napoli et al. And Meyer. So it's statistical strategies to remove the outliers. And this is done per hour and per morphological unit in terms of how we know the weather translates into patterns here. So basically, we do not do the statistics to the full area. We do by subgroups that we know that have equivalent weather patterns. This in the background is the weather services forecast in Lisbon with the 2.5 kilometers pixel resolution, and this is done for the full country, actually for the Iberian Peninsula, but we wanted to upscale it and to improve it in terms of resolution to show the city. So basically we have official stations and at-atmos stations after quality control as our response variable. We have as temporal varying conditions, the forecast from the official weather services, not only temperature, but surface level pressure, relative humidity, and wind. Wind is very important, as I mentioned, because every kind of thermal fluctuation near the surface is a function also of how sheltered a given place is from the prevailing northern winds. And then you have the landscapes effects, which are related to this, basically topographic exposure as a function of prevailing wind at a given time. This is interconnected. And you also have the gradient in terms of coast and river distances that changes throughout the day according to the coastal breezes and the land breezes variations throughout the day. And then you have the urban proxies, basically Bowen ratio as a function of fluxes, imperviousness, and tree cover. So I replicated the random forest here, but with other inputs and other target outputs, but the rationale is basically the same as in Naples. Sorry. And we were able to upsample from 2.5 kilometers to 250 meters in terms of spatial resolution. Not only that, but also the pattern becomes much more interesting in terms of municipality, in terms of the municipality, in terms of actions, in terms of heat exposure. So you go from this, which is the state of the art in terms, official weather forecast for Lisbon, to this. And for you to know, this is a green park, a very large green park over here. This area that you see here with low density is very subject to oceanic breeze, and you can see how the model accounts for both the natural and the artificial influences of over temperature. And for those of you that might know Lisbon, you can see that these warmer areas are, follow the most dense areas of the city. So LCZs 2 and 3, because we don't have LCZ 1. We don't have very high-rise buildings. This is another example for the southern part of Lisbon, which is still in validation stage. And you can see here the slow gradient in terms of the official forecast after interpolation, and how the model emphasizes some very inland dense neighborhoods that are near here the highway, and how this translates not only into a greater level of detail, but improve accuracy in terms of temperature. This is another example also in the Lisbon area for Cascais, in which we translate the temperature into exposure as a thermal amplitude proxy to highlight which areas or neighborhoods are warming in each time of the day. And here some errors reporting the performance of the model. And here you can see the overall improvement in every season compared to the state of the art or official our own predictions. In addition to this, we have developed a platform. The platform is currently live, and I can put here in the chat the link for you to check it. It's of course just a beta phase, so we are trying to put the model into production, see how it behaves. This is not a physical model, it's a machine learning model, and this means that the model cannot predict accurately anything that he did not acknowledge in the training data set. And this is very important in terms of future climate scenarios, but it can provide like a glimpse of how things work. So far, in terms of accuracy, we have been a positive gain in terms of precision compared to the AROM model, if we compare the AROM and our model to observations. And this is basically open to the community, and we are trying to establish partnerships to complement the temperature and translate it into indices. So what we want to do next is to get together with our early adopters and see which kind of indices are of added value to them based on the temperature, because the temperature itself is not, valuable. It is, but is more meaningful if we translate it into proxies of risk. So basically what's on the table right now is temperature anomaly for climate monitoring, excess heat factor, which is the index that I previously mentioned, that can highlight which regions of the metropolitan area are more at risk of health impacts, and this can be multiplied but by the number of elderly people again, but at another scale, and the cooling and eating degree days to see the spatial patterns of the temperature variation in terms of energy consumption. Another application of this that is being discussed is to produce the scenarios that I mentioned earlier, to basically introduce what kind of urban planning strategies are being discussed at the municipal level, where they want to introduce green parks or new neighborhoods, dense neighborhoods, and to check how the model behaves in terms of replicating what kind of hotspots or cold spots can arise from these changes in urban development. And these are just some scenarios that I did for Lisbon in this regard. And I'm already concluding. Our next step, as I mentioned, is adding more added value layers. Check with our early adopters how meaningful they think this exercise is, because if this does not get adopted, it's not useful, and we want it to be useful. And we already also submitted with Almada, one of the municipalities here, a grant to produce a mobile application that is based on this model and this layout and this kind of rationale. And we basically want to reach out to the community and something that can be used by all the citizens to become aware of how exposed they are in a given neighborhood compared to others. And with this, I conclude my presentation. As I said in the beginning, please feel free to reach out should you have any question, any issue you want to discuss. And I'm open to questions now also if you have the time. Thank you. Thank you.
Let's see for maybe a short question, because Manavi is next and she's here. Yep. Does anyone has maybe a question or a comment about the work or about Anna's way to become so brilliant in GIS, because we have here smart GIS people. So Anna, can you give maybe a short advice to our young GIS colleagues, for example, how to obtain some good practical skills, and do you have maybe some trick? You said for some things you got lucky, but of course it's not just a lot of work.
Okay, so for me, a game changer was learning R. I know that a lot of people go to Python instead of R. I did R because I think it's a bit easier. And as I said earlier, I was not a programmer or a GIS expert, so I have to learn everything myself. What I would advise is for you, as much as possible, to adhere to code instead of GIS platforms, especially paid for. This would be my advice, because it gives you much more flexibility in terms of replicating, computational capacity, etc. And it's a very sought after skill. So in terms of also of job opportunities, etc., it's a game changer compared to traditional GIS based approaches. I mean, I use QGIS or ArcGIS for visualization to produce maps, etc. But in terms of hard work, modeling, etc., I think that Python or other equivalent would be my best advice in terms of hard skills.
Perfect. Yeah. So I hope you heard. Yeah, they know. I think they will have some basics, but of course they need to work more, because as you mentioned, who has these practical skills, and really there's no barrier to becoming successful and having, you know, good lifestyle and salary and so on. There are lots of free tutorials, courses, and so on. Just how much you want to sit.
Yeah.
In that regard, once more, thank you for the great presentation. Also, Manavi wrote this was a very insightful presentation. And if there are, of course, any additional comments or questions from our colleagues here, I will, if you agree, give your contact.